95% CPU. Nothing in your logs, nothing in your metrics, nothing in your traces. You know something is wrong, but you have zero visibility into what your code is actually doing in production. This is the visibility gap. And in the last few years, one Linux kernel technology has completely solved it. It's called eBPF, and it gives you X-ray vision into every process on every server. Traditional observability gives you 3 signals. Metrics tell you that CPU is at 95%. Logs tell you what requests came in. Traces tell you how long requests took. None of them tell you why the CPU is at 95%. Is it the garbage collector? A slow, regular expression? A tight loop that nobody noticed? To answer the why, engineers used to attach a heavy debugger, restart the application, and try to reproduce the issue in staging. By the time you've set up your tools, the spike is gone, the user has refreshed, and the problem looks invisible. That was the state of profiling for 20 years. eBPF stands for Extended Berkeley Packet Filter. The name is misleading. It has very little to do with packets anymore. eBPF lets you run small, safe sandbox programs inside the Linux kernel itself. No kernel patches, no kernel modules, no application restart. Think of it as a programmable hook the kernel exposes to trusted observers. Here's how it actually works. You write a small program in a restricted subset of C. The kernel passes it through a verifier, a static analysis engine that checks for infinite loops, illegal memory access, and unsafe calls. If verification fails, the program is rejected. If it passes, the kernel JIT compiles your bytecode to native machine code. Then it attaches your program to a hook. For profiling, that hook is a hardware timer that fires 99 times per second. On every tick, your eBPF program runs, reads the current call stack, and writes it to a shared memory map. A user space agent reads the map and ships the data to a backend like Parker or Pyroscope. Total overhead, under 1% CPU. Now combine that with continuous profiling. Instead of running profiling only when you suspect a problem, it runs 24/7. Every process, every container, every server, always. When the OOM kill happens at 3 a.m., you don't need to reproduce it. You just rewind the tape. You open the profiling UI, scroll back to 2:58 a.m., and see exactly which function was allocating memory before the kernel killed the pod. The other huge win is zero instrumentation. You deploy the profiling agent as a Kubernetes daemon set, 1 pod per node, and it immediately sees inside every process on that machine. No SDK imports, no library upgrades, no application restarts, no code changes, regardless of programming language. Go, Rust, C++, Java, Python. They all show up automatically. All that profiling data is useless without a good visualization. The standard is the flame graph, invented by Brendan Gregg at Netflix. Once you know how to read one, you'll never look at performance data the same way. 3 rules. 1. The x-axis is not time. The x-axis is the proportion of samples where that function appeared. Wide bar means that function was on the CPU a lot. Width equals cost. 2. The y-axis is call stack depth. Bottom of the graph is the entry point. Each layer above is a function called by the layer below. Tall stack does not mean slow. It just means deep call chain. 3. Color is just category. Red is not bad. Red usually means kernel code. Green usually means application code. Color is for grouping, not severity. The diagnostic rule: find the widest bar that has no wide children. That's your bottleneck. It's spending time doing work itself, rather than delegating. That's where you optimize. Tall and thin? Irrelevant. Wide and short? That's your problem. One last thing that trips people up. CPU profiling and memory profiling answer different questions. CPU profiling samples what's running on the CPU right now. It finds hot loops, slow regular expressions, busy work. Memory profiling has 2 flavors. Allocation profiling shows where memory is being created, useful for reducing garbage collector pressure. Heap profiling shows what memory is still alive, useful for finding leaks. A Go service that grows by 50 megabytes per hour and never shrinks? That's a heap profiling problem, not an allocation problem. Allocation churn shows fast create and destroy. The leak shows up only in what's still alive, so the playbook. Latency regression after a deploy? CPU flame graph. Look for the widest bar that wasn't wide yesterday. OOM kill pod. Heat profile from a few minutes before the kill. Look for the function holding live memory. Mystery slowdown that comes and goes. Continuous profiling with differential view. Overlay this hour against last hour. Anything that got fatter is your suspect. eBPF profiling is becoming standard infrastructure. Parker is open source. Pyroscope is integrated into Grafana. If you're operating production systems in 2026 and you don't have continuous profiling, you're flying blind. Start with one daemon set and you'll have X-ray vision inside every process you run. We cover this in depth at hamchops.com, link in the description.